The diffraction grating sorts light by wavelength, rather like a prism, yet it is flat. It has many lines that alternate between transparent and opaque. Thus it is like having a large number of closely and evenly spaced slits. When light shines on the grating from the left, each opening acts as a source of wavelets that is capable of interfering constructively or destructively with its neighbors. The light falling on the screen to the right show as isolated points of high-intensity constructive interference separated by vast areas of destructive interference. Constructive interference occurs when each path to the screen differs by one full wavelength from the neighboring paths. Mathematically, this condition is met when d sine theta is equal to m times lambda, where m is an integer. Since the spacing d is small, 1/750,000th of a meter, the angles for constructive interference are quite large. No small angle approximations will work here, so we get the angle from the inverse tangent of the distance along the screen from the central bright spot, y, divided by the distance from the grating to the screen, L. Knowing y, L, and d allows us to determine the wavelength of the light, lambda. This picture shows the laser light striking the grating. If you mark the central bright spot and the two first-order maxima on either side, you can measure y as half the distance separating the two side maxima. Remember that L is measured from the grating to the screen. We can use a CD as a type of reflection grating. The CD has pits arranged along spiraling grooves that are separated by a small distance d to be determined. When laser light is reflected from the surface of the CD, some reflected angles will give rise to constructive maxima in intensity, just as it did for the grating. Place the laser at a height such that its beam will strike the CD at a point where the grooves are oriented vertically. Place the screens where they will catch the reflected light. Stand the CD up using the slotted foam. Take some care to send the direct reflection straight back at the laser. The bright spots on either side are the first-order maxima. Measure the distance L from the CD to the screen, and measure the distance between the two wide spots. Divide this distance by 2 to get the value of y. Use the wavelength L and y to get the groove spacing on the CD. The double slit has only two somewhat closely spaced sources of coherent light that interfere with one another. Maxima in intensity occur again whenever d sine theta equals m lambda. Because the slit spacing d is not as small as for the grating, the angle between interference maxima is also small. Now we can use the small angle approximation such that the sine of the angle is close to y over L. The wavelength lambda equals d times y divided by L. The setup is similar to that for the grating, except the distance L must be larger to make y measurable. The intensity maxima are now closely spaced. Use a pencil to mark the locations of 10 adjacent spots. Measure the complete distance and divide by 10 to get y. Light passing through a single slit interferes with itself in a process called diffraction. Minima in the intensity pattern occur when there is destructive interference between sources separated by only half the slit width. Thus, a over 2 sine theta equals m lambda over 2. The 2's cancel and the angle is small, so we find that the slit width a is a product of lambda times L divided by y. We set it up as for the double slit, with L quite large. Locate the two dark spots on either side of the central bright spot. From y, L, and the wavelength of the laser, determine the slit size, A. When light shines through a circular aperture, a circular diffraction pattern of concentric rings is formed. The angle in radians of the centered bright circle is given by 1.22 times the wavelength divided by the diameter of the aperture. A similar diffraction pattern emerges when light strikes a collection of randomly placed circular obstacles. We will place Lycopodium spores on a microscope slide and shine a laser through. The angle is found from the ratio of the radius of the bright spot r divided by L. Knowing the wavelength of the light, we can determine the diameter of the tiny spores. Dip the slide into the powder to give it a light coating of spores. Place the slide in the slotted foam. Shine the laser through the powder, and the diffraction pattern is viewed on the distant screen. Trace the outer edge of the large, bright central region, then measure its radius when you have more light. In 1923, Louis de Broglie hypothesized that electrons travel as waves with a wavelength given by h divided by momentum. In this experiment, an electron beam will be aimed at a graphite crystal, which will act as a diffraction grating for the electron beam. The diffraction will appear as circular rings of interference maxima on a fluorescent screen. The speed of the electrons in the beam is determined by the accelerating voltage, capital V, on the electron gun. We find that the de Broglie wavelength of the electrons in nanometers is just the square root of 1.505 over V. Measure the accelerating voltage to give the wavelength of the electrons. When the beam is reflected off two adjacent levels of the crystal, the condition for constructive interference is that 2d sine theta equals n lambda. The hexagonal graphite crystal lattice presents two spacings to the incident electrons. The smaller spacing leads to a larger diffraction ring. Here is a schematic of the apparatus, though you should probably let your lab instructor set it up for you. The electron beam must never exceed 0.2 milliamps, or the crystal may be destroyed. You're free to watch me set this up or fast forward, your choice. The angle for constructive interference is determined by measuring the radius r of the diffraction ring and the distance L from the graphite crystal to the screen. Because this is a reflected beam, it suffers a reflection of 2 theta. You may just use a ruler to measure the radius of the outermost ring. Using the outermost ring will give you the smaller of the two spacings in the graphite crystal. Using this technique, you'll have measured a size comparable to the size of a single atom.